so let's see where we left off. I had to split 4.5 into 2 days, so hopefully today we can finish 4.5, and that will allow us to get to 4.6 by tomorrow and give you the weekend to work on your homework. And then Monday in class, you can ask any questions over any homework questions. Your homework will be due by 5 o'clock on Monday. So we started with looking at optimization problems. We want to optimize or minimize surface area, volume, cost, revenue, all these different things we can maximize and minimize. I can maximize the volume with minimize the surface area type problems. In this case, we did a garden problem where we had 100 feet of wire and we wanted to find the maximum area. And some of us, I don't know if this class, you guys made the assumption, or eventually you thought the maximum area is going to be when you have a square. And it turns out, given a length and a width, the maximum area of a rectangular is always going to be a square. So in this case, going through, you need to show the algebra, you need to show the calculus. Going through, differentiating this, I get x equals 25. So if x is 25, I can plug that into my formula for y to find y is also 25. I can test I have two methods of testing to see if it is a true maximum or a true minimum. I can do the second derivative test, find out it's concave down, so that point is going to be a maximum. Or I could do testing the endpoints and also testing the critical point, finding out that this is a maximum. The procedure we talked about for any type of problem on here, you're going to draw a picture. So you need to be comfortable drawing cones, spheres, circles, rectangles, things like that. Knowing formulas for them. If it's anything other than like a rectangle area, I'll give you the formula. And we'll see some examples in Wiley. If you push the hint button, it gives you the formula. We'll do an example of a cone. And the volume of a cone you have to know is pi r squared, or pi r squared times L, which is the lateral surface area, or the lateral slant of a cone. So getting familiar and comfortable with the types of problems that would potentially be asked, that's where kind of the formula comes in. And if we have time, I can pull up some old final exams and show you what problems come from this section and what they look like. The ones you do on Wiley will be, the level of difficulty will be just a little bit higher than you'll see on a final exam or the exam. Step 3 is to write the function in one variable. Usually from the picture and the formula, you have two equations and two unknowns. So you can solve for one of the variables in the equation that's given, plug that into the equation you want to maximize or minimize. And when I say given, the information is given to write it. You're very rarely given an equation. And then step 4 is to think about the interval. So when does it make sense for the function to exist on your one variable? So you want to state that out. And then find maximum and minimum. And by finding the derivative, setting that equal to 0, and either testing your critical points or doing your second derivative test.
Excuse me, like looking for the maximum or minimum, we can use either the first derivative test or the second derivative.
If there's only one critical point and x cannot equal 0 or x cannot equal 50, you have to do the second derivative test. Or you could do the first derivative test if you have it. This is not the first derivative test, though. This is just plugging in points. And that only works on a closed interval. But you could do the first derivative test to see that this is a maximum. But you have to be careful. If I did the first derivative test on this closed interval, and in applied problems, a lot of times the bounds are 0. But in non-applied problems, you can't just do the first derivative test. If I had an example of a graph of a function that looks like, let's say, looks like this. If I do the first derivative test here, I have that it's a maximum, but it's not the global maximum. This is. So I have to still test the endpoints. Question? Oh. Does that make sense? So in this case, if I did the first derivative test, I would get that as a maximum, but that wouldn't be enough proof to say that if I plug in 0, that's not going to be even higher of a maximum. It's a local maximum, and if you only have one critical point, a local maximum is the global maximum, right? That's in an open interval. This is a closed interval, so you have to test your points. Or you can just do the second derivative test when you only have one point, right? In the application problems, it works out because I know if x is 0, then my area is 0, and if I know x is 50, my area is 0, because y would be 0. But in general problems, you can't assume that, so you have to test those endpoints. We did the example of the piece of sheet metal. If I stamp out an x squared from the corners and fold that up, finding maximum volume. And again, testing those points. We looked at the can that holds 1 liter. Even though our numbers didn't come out too nicely, we found out that anytime you're going to minimize the surface area given a specific volume, your radius is always going to be 1/2 your height, or your height is going to be twice your radius. So on Wiley, when you get to problems like that, and they give you a specific volume and want to minimize your surface area, and you find a radius and you find a height, to kind of check yourself, you're going to check that the height is twice your radius. Hopefully your numbers work out a little nicer, because this is kind of hard to see. And if I write it nicely, you can see it, but getting from here to here is some algebra. And we talked about that in class. You can plug it in your calculator and get an approximation. And plug the height in your calculator and get an approximation and see if it's twice the original approximation. But Wiley wants you to put in an exact answer. On an exam or on a final exam, your numbers will come out nicely. I'll just say that much. So, I mean, we have to grade these, so it comes out where it's not anything too ridiculous.
So we can't just use that as proof and say we know that.
Well, you would have to find one. You don't know what the height is going to be or the radius is going to be.
Oh, that's true.
For this specific example, for 1,000 centimeters, it's going to turn out to be this number. But for the one that you have on Wiley, it's randomly generated anywhere from, so no. But once you find the radius, you plug that in for the height, you should expect it to be,
Right.
the height be twice the radius. Yeah, so I think it's, not that one. So this one, this is randomly generated, right? So 650 is different, so your radius is going to be different. But once to check your answer here, you should expect the height to be twice the radius. So then we said, these definitely can get difficult. This can get complicated. And so we looked at this example. We took, find the radius and height of a right circular cylinder with largest volume that can be inscribed in a right circular cone. So I might have plastic molds that have this certain shape. And I want to go in there and I'm going to machine out a cylinder from this mold. And I want to make sure that my machine part is going to have maximum volume. So I'm going to use the most amount of this plastic I can get out of it to get a right circular cylinder. So, I mean, mechanical engineering type applications here are pretty plentiful depending on what you want to do. So setting this up, I ran out of time in class, so we're going to begin with this one. This looks a little dark. Okay, so let's see what we get here. We have a So I drew this picture, and I don't know, I didn't get to the point of really explaining where this relationship comes from. I want to maximize volume. So this is my formula for volume. You can see that it's a function of R and H, which gives me problems. I need to get it as a function of only R or only H. So I need another relationship between H and R. And I get that by similar triangles here. So if I take out a slice of this cone, this is the height of my cylinder, and this would be a maximum of 10. This is the radius of my cylinder, and it has a maximum radius of 6. Right? So here I can say 0 is less than equal to r is less than or equal to 6 for the radius. Or I could say 0 is less than or equal to h is less than or equal to 10 for the height, depending on if I'm looking at the volume in terms of r or if I'm looking at the volume in terms of h. Do you guys see where that comes from? Okay, so using similar triangles, I need to find a relationship between h and r. And so I can say this distance here would be 10, but I need it as a function of h. So I can say various different ways. I could also write it as a function of r. Similar triangles, there's multiple ways to look at it. The way I set it up is I said 10 minus h is to r, which would be this distance, right? The smaller triangle's height to the smaller triangle's radius is going to be the larger triangle's height to the larger triangle's radius, right? So I needed to get h, I needed to get this distance as a function of h. I couldn't just use h. Question?
Wouldn't 10 minus h be the part that's not h?
If I take 10 and I subtract h, yeah. So it would be this dotted line is to, let me go back here. So this would be 10 to 6 is h minus 10? Do we want to put h minus 10?
Or 10
No.
minus h and then
But then it would be,
minus r?
let's see where I'm at.
Or 10 minus h.
Okay, so I want to set this up differently. I want to call this, yeah, so this distance here is h, and this distance here is 10 minus h. So this distance here is r. Right? So now I have the triangle up here. That's the smaller triangle that's similar to the bigger triangle. Right? Because this is not a triangle. That was my problem. If I use h, h would not be a triangle. So I need to use a triangle. So this is my triangle here. So I have 10 minus h is to r as 10 is to 6. Do you guys see that now? Sorry about that. I need to use a triangle, not a triangle that's head's been cut off. So I have this relationship. So if I solve for h or r, what would I have? I would have 60 minus 6h equals 10 times r. What? So I have a choice. I can solve for h or I can solve for r. Honestly, it does not matter which one you do. Generally, there's one that's a little bit easier to plug back in. And can you see which one's going to be easier to plug back in? H, right? Because h is not squared. The r would be squared. But so I want to solve for h, so then I would have minus 6h equals 10r minus 60. H would equal 10 minus 10r over 6, which would equal 10 minus 5 over 3r. So doing some switching around and dividing by 6, this is what h is. At that point, you've really done the majority of the work. The majority of the calculus. Well, majority of the setup. You haven't got to the calculus yet. So now my volume is going to be pi times r squared times 10 minus 5 over 3r. All right, because that's h, and h in terms of r. So I can rewrite this 10 pi r squared minus 5 pi r cubed over 3. So that's my volume function, and I want to maximize this. So I need to take the derivative and set it equal to 0. Do you guys see what I did here? So I'm dealing with r, so I'm going to keep in mind that the interval would be less than or equal to 0 less than or equal to r less than or equal to 6. If I would have dealt with h, I would have a little bit different function, and then I would keep in mind the bounds on h. So what is the derivative of this function? So this is a quadratic. You guys can solve for a quadratic, right? So if I write this as minus 5 pi r squared plus 20 pi r, I could use the quadratic formula. Or I could factor out an r and have 20 pi minus 5 pi. I'm going to factor out more than that. Let's factor out more than that, sorry. Let's factor out a 5, pi, and an r. So I have 4 minus r equals 0. So r equals 0 or r equals 4, which both fit in my interval. I use Pythagorean's theorem with a quadratic as well, but it turns out it's easier to factor it because I factor out 5 pi r and I get this one. So now I need to test my points. What is the volume when r is 0, the volume when r is 4, and the volume when r is 6? 0 and 6 is easy, right? Because I have no height if my radius is 6, and I have no radius if my height. Sorry, I have no height if my radius is 6, and I have no radius if my radius is 0. So if I plug that in a volume formula. So now here as r is 4, I can plug it into the volume formula for specifically r, or I can find h and plug it back into the original volume formula. I don't know what's it asked me. It just asked me for the maximum volume, so I don't need to find h. Right, I already have a formula for volume in just terms of r. So it turns out if I plug this in, I get 160 over 3 pi. So this is the max volume. Max volume occurs when the inscribed cylinder has radius 4, and it turns out the height would end up being 10 over 3 if I want to calculate that. If I come back and plug in 4 here for r, the height would be 10 over 3.
Excuse me, the r equals 4, is it negative?
No. What?
Like when you plug in 4 back into the equation?
4 back into this equation? This equation? I could plug it in this equation as well. Then it definitely is not negative. Volume cannot be negative, right? So, what? What would I get here? I would have 16 times 10. What would I have? I would have calculator. If I plug in 4, I have 10 times 3.14. Well, let's leave out the pi. So I have 10 times 4 times 4 minus 5 divided by 3 times 4 times 4 times 4. Yeah, so that's not negative. It's 53 point something. Okay, I'm just plugging 4 into this formula, and it's not negative. Any questions on that?
So we have to plug it into the one that you factor?
You don't have you have to find the volume. You have two options to find the volume. You can go back to this original volume problem, and if you have r is 4, you can plug 4 back into the h problem to find h, and then plug in r is 4 and h is 10 over 3 and get your volume. But you've already done the work to solve for volumes in terms of R only. So volume is a function of only R. So if you know R, you know the volume. Right?
Okay, so because we solved for R down there when we were testing the points, then that's why we plug it back into the volume function in terms of R only.
Yes.
Okay.
You could plug it back in the terms of the volume function of R and H, but you'd have to solve for H.
Right.
So depending on what they wanted. If they wanted you to solve for R and solve for H, then it doesn't matter because you've already have to do that. But if they just want the maximum volume is this, and it occurs when the radius is 4 and the height is 10/3. For different, height here and radius here, your problem's going to be a little bit different. But the method of doing it is the same. You find the formula for volume, so volume pi r squared times h for a circular cylinder. And once you know that, you need to get, this is in terms of only r or only h. So you need to use similar triangles. You actually have to use a triangle here. So set up the relationship between r and h here. Then you plug the term for h as a function of r. So here h is a function of r back into for h, and then you have a volume function of r.
So if you want to plug in R back into H,
This is
the R in the other one, like H equals to 10
Yeah.
minus
This
Do we
one?
have to plug in 4?
Yes.
R?
Yes. To find what h is when r is 4. So you're finding what is the height of the cylinder when the radius is 4. Okay, so let's look at some problems that are on Wiley that will come up on your homework. Keep in mind these are randomly generated, so the problems I do might slightly be different than the problem you do, but the method is going to be the same. So let's look at the first one. This is number 9. And I want to find the dimensions of a rectangle that's inscribed in a circle with radius 8. Majority of the times the students, the algebra is what gets them. They can set up the problem, they can do the calculus, the derivative, but setting the derivative equal to 0, they don't know how to go about and solving for that. So this is 4.5, number 9. So the first thing you want to draw is a picture. I have a circle, and I have an inscribed rectangle in the circle. And I want to maximize the volume of my rectangle. So what's the formula for volume of a rectangle? Or sorry, area. Area of a rectangle. What? Length times width, right? So let's say length times width. So I'm going to call this the length, and I'm going to call this the width. So what do I know about my circle? It has a radius of 8. So what would this represent? The diameter, 16. So now do you see a function that I could relate to the circle with the length and the width? Pythagorean's theorem, right? So I say the width squared plus the length squared is 16 squared. 2 equations, 2 unknowns. You always need that second equation because now I can solve for W or L in terms of the other one, plug that back into my area function, differentiate that, set it equal to 0, and then maximize or minimize it. So which one do you want to solve for? Length. So the length here is going to be 16 squared minus W squared, the square root of that. We're dealing with distance, so we can ignore the negative one. So I solve for length. I plug that back into my area formula. So I have area is the square root of 16 squared minus W squared times W. This is the function I want to maximize. The procedure on all these are the same, right? Get the formula or get the picture. Get the 2 formulas, write one formula, solve for one variable in one formula, plug that back into the formula you want to maximize or minimize, and then maximum minimize it. So here, what is the derivative of area? Derivative of the first one, hold the second one, plus the derivative of the second one, hold the first one. So this would be the square root of 16 squared minus w squared plus w times 1/2 square root of 16 squared minus w squared. Oh, sorry, that's to the minus 1/2. What am I missing? The derivative of the inside. That's probably the most common mistake in these types of problems. Forget to do the chain rule here. So I'm missing minus 2w. So at this point in calculus, you should be somewhat comfortable taking a derivative of a function like this. So I'm going to write this a little nicer. Minus 2w squared over 2 the square root of 16 squared minus w squared. So the 2's cancel. And I'm going to set this equal to 0.
Is that one, the second one, not under the square root sign?
This one, well, it would be minus the 1/2, right? Because the derivative of the outside would be 1/2 the inside to the minus 1/2. It's just in parentheses. Yeah, I'm sorry about that. I used to have white out my bag, but I don't anymore. So yeah, just, it's not under the square root, so.
So the sign inside is in multiplication of minus?
Here, this is minus. Question?
And you're not using the product rule, you're just like integrating the set.
Here I'm using the product rule. The derivative of the first one, I switched. The derivative of w is 1. Hold the second one, plus the derivative of this one, which would be all this, hold this the second one.
So in these types of problems, do we always use the product enclosure rule?
You're just differentiating it. So if it calls for a product rule, you have to use it. So I'm asking for the derivative of this function, which is a function times a function. So use the product rule. Sometimes you can get away with foiling it out and not using a product rule. A lot of times, the example we did last time with the sheet metal problem, we end up with a function like this. I could use the product rule, the derivative of the first one, hold the second two, but it would be cumbersome to do that. So foiling it is relatively easy, and differentiating a polynomial is straightforward. So I wasn't forced to use the product rule here. But in this case, I don't have a way around it, right? So the derivative of w is 1, hold this function, plus hold w times the derivative of this function. And the derivative of this function is 1/2 the inside to the minus 1/2 times the derivative of the inside.
Would it be a shorter way if I cancel the square root and like I have 16 minus w times w?
Cancel the square root and you have 16.
Are they both squared?
You cannot do that. That's extremely illegal. A squared plus b squared, the square root of that does not equal a plus b. There's some branches of mathematics this is true, but in the Euclidean coordinate system we're in, this is not true. Okay. Question?
You just multiply both sides by the square root of 16 squared minus w squared.
At this point?
Yeah.
Yes. Yeah. So moving along here, I multiply both sides by the square root of 16 squared minus w squared. That gives me 16 squared minus w squared equals 0. Because 0 times anything is 0, right? A little bit iffy on here. What did we define w to be? Did we give a what are our bounds on w? Because I want to make sure I'm not multiplying through by 0, right? That would be bad. So let's say w could be 0. What is the maximum w can be? 16, right? So if I include 16, I could potentially be multiplying by 0. So here it turns out I have to include that it's the open, right? But at this point, we should be able to solve for when it equals 0. What do I have? Minus 2w equals minus 16 squared. So w equals the square root of 16 squared over 2, which would be, 16 over square root of 2, which would equal the square root of 128. It's, yeah, negative 2w squared. Thank you. Keeping you guys on your toes today. Question?
Does that equal square root of 128 at the end, or is that?
It does. So I did this one in the last class period, and it turns out here I can write this as 16 times square root of 2 over 2, right? It turns out 16 squared is 256. So this could be 256 over 2. 256 over 2 is just 1 over square root of 1 over 128. Square root of 128.
Is it more convenient?
Any way you write it, Wiley will accept it. This will be nice because it turns out when I go to find length, it's going to be the same thing. It's the square root of 128, which is exactly what we expected, right? Maximum area for a rectangle is going to be when that rectangle is a square, when length and width is the same. So I know the length formula is the square root of 16 squared minus w squared. So if I take the square root of 16 squared minus 128, or square root of 128 squared, that gives me the square root of 128. 16 squared is 256. But I could have left it as the square root of 16 squared minus 16 over square root of 2 squared, and that's going to still give me 16 over square root of 2. So if I come over here and I put this in as the square root of 128, and I put this one as 16 over square root of 2, these are the exact same thing. Wiley should accept both answers. Oh, that's supposed to, oh no, it's right, okay. I was like, oh no, it's supposed to be squared, but it's not. Okay, so if I go to a calculator, let's take 16 divided by the square root of 2, and let's take what is 128 squared. You guys see that this is the exact same thing as the, not that. What happened there? The square root, I divided it by the answer. So here, 128. Square root of 128 is the same thing as 16 over square root of 2.
So we are looking for the width or the length. I don't know.
You're looking for the length and the width of the maximum rectangle. And the maximum rectangle is going to be when the length is 16 over square root of 2 or the square root of 128. Just different algebraic ways to write that. But any way you put it in Wiley is fine as long as it's exact. If you put it in a decimal, that's not exact, though.
What did you say about it always being square?
So it turns out when you have a finite perimeter, which in this case you do, then your maximum area is always going to be square. So if
And that's what this is.
and this is another illustration of that, right? We did the garden problem. If I only have 100 feet of chicken wire, and I have to enclose a garden, it turns out the maximum area is when the garden's a square. The same thing in layouts in rooms. If I have, X amount of money to build a wall, and I want to maximize my area, my room's going to be a square. Right? So let's look at another problem on Wiley that comes up a lot, and I want you guys to work on this one. I've seen this come up. I've seen this come up on final exams. we have a closed rectangular container with square bases. So square base. The volume is 4,394 inches cubed. So I have to have a specific volume. I'm going to pour some chemical in this, and it has to contain this much chemical. But the material that I make the top and bottom for is going to cost different than the sides. So it's kind of like I'm going to fence in a fence, and maybe I want to maximize my area, but my fence doesn't cost the same. I might have to make a fence that on one line of my fence it might be made out of more expensive material than the other two sides. So in that case, your area, your cost function is going to, the area is going to depend on your cost function, so it's not going to be a square. So here it cost me $4 to make the top and bottom of this container, and it cost me $2 per inches squared to make the sides. And I want to minimize the cost it takes me to make this container. So this is number 22. The very first thing you do is draw a picture. And hopefully your picture looks better than mine. So, and we also write down the formula that we know. We know that the volume of this container has to be 4,394. It costs me the top / bottom is $4 per inches square, and the sides are $2 per square inches. So this is what I know. Hopefully my container can hold something. It told me that the base was square. So I know that's x times x. So the volume of this container is x times h. So then I know this is going to be x squared times h. What do I want to minimize? The cost, right? So I need a function for cost. So cost, how much does it cost to make the top? Very good. 4 times x squared. And how much does it take to make the bottom? 4 times x squared, right? So I have 2 of those. So I have 2 x squareds, and that cost me $4, right? The area of the bottom is x squared, the area of the top is x squared, and it cost me $4 per square inch to make those. Plus, how many sides do I have? 4. What's the formula for the area of the sides? And how much does it cost me to make that? $2. So this is my cost function, right? Now that I have my cost function, this is the function I want to minimize, but I need to get it all in one variable, right? And it's mostly in one variable except this h. So I need to find a formula, or I already have it written down, that I can solve for h in terms of x, plug that x in for h, and then differentiate and go from there. So here if I solve for h, what do I have? So I have h as a function of x. Given this h is a function of x, I plug it in for my cost formula, or my cost function, and I get 8x squared plus 8x times, right, because this is h. So cost would be 8x squared plus whatever 8 times 4,394 is over x. So here, my bounds on x has to be greater than 0, but it cannot equal 0. And then it also has to be smaller than infinity, right? Because this would go, I only need to make sure that I have a volume, so I can pick a larger and larger h, or x, then my h is going to be really, really, really small. So this is an open interval type problem, right? So I have to do a little work if I only have one critical point. Because I can't plug in 0 and I can't plug in infinity. So what do I want to do to the cost function to minimize it? Yeah, I can find the derivative. So what's the derivative of cost? That's 16x minus 8 times 4,394 over x squared. Set that equal to 0. So how do I solve for this? I can multiply through by x squared because x doesn't equal 0. So I don't have a problem doing that. So I end up with 16x cubed minus 8 times 4,394. That equals 0. So I have 16x cubed equals 8 times 4,394. X cubed equals 8 times 4,394 divided by 16. So then x equals the cube root of that. Does someone with a calculator want to plug that in? And hopefully Wiley is nice to us and gives us a nice, pretty number. $13. Anyone else want to confirm that? So x is 13. Well, if x is 13, what is h? Well, if I come back here, I already solved for a formula for h in terms of x. So I have h is 4,394 over x squared. X equals 13. So h would be 4,394 over 13 squared, which is what? 9? 4, 3. Oops, didn't put that in right. 4, 3, 9, 4 divided by 13 squared, 26. 26. So I forget what the problem asked. What did it want? It wanted the length and the height. So we saw that this was, the length is 13 and the height is 26. And I could check myself here because the volume was given, right? So I need to make sure that 13 times 26 was the same volume that was given. Turns out it is. So I can submit there and we're happy. Question?
Oh, well, I think it was pretty apparent, but we didn't really, did we like check for minimum or anything on that one, or did we kind of just look at it and say its behavior is 0 and infinity is such?
Yeah, so that is a good point. For this function, it's a quadratic that opens up, so the critical point is the minimum, but I would probably still need to say that to verify that, to check that. So another way I could do it is I could, let's see, could I,
It wants to minimize costs so that you know it's not.
you can't always assume that. So yeah, you could say this is a minimum because graphing this function, it's a quadratic that opens up. You could also do the, at 13, do the second derivative test to see that it's concave up. If I take the derivative of this again, and I plug in 13, that it's positive. So it's concave up, so it's a minimum. So what would be the cost? Second derivative would be 16 plus 8 times 2 times 4, 3, 9, 4, all over x cubed, which is greater than 0 when x is 13, right? So concave up. It's a minimum. So yeah. A lot of times in application problems you get quadratic. So you're going to get one critical point. So it's either a quadratic that opens up, so it's your minimum, it's a quadratic that opens down, it's your maximum. So sometimes we forget to kind of play lip service to verify it's a maximum or a minimum. So a lot of times if we want you to do that, we'll give you find a maximum and minimum and verify it or something to give you that hint to, oh, I need to go ahead and check the second derivative, or at least make a point that this is a quadratic that opens up or quadratic that opens down.
How did you know on the first one that it was conjugated? That we gave the
This one?
rectangle on the circle.
This one, number 22, the
The number 9 that we get, the number.
oh, number 9 here. Well, we didn't have to worry about that because it's a closed interval. So I can test my endpoints, right? When I have a closed interval, the extreme value theorem states that the extreme value is going to be a critical point or an endpoint. So this is a closed interval. So I can test my points to be 0, which I know that the area is going to be 0, or 16, which I know the area is going to be 0 because my width would be 0. So the critical point in here is going to be the maximum or minimum point. Do you have to test? And since it's 0, it's going to be a maximum because you can't have negative area. So when on a closed interval, it's a lot easier because of that extreme value theorem. Test the endpoints and test the critical point. The largest one of those three is your maximum, and the smallest one of those three is your minimum. Of course, the smallest area you can have is 0 because area can never be negative and distance can never be negative. So we don't have too much time, but I want to point out the problem, the third problem. This is definitely quite a bit more complicated because there's really 3 equations, 3 unknowns that you have to substitute for. So let's look at starting this one. We probably won't finish it, but it will give you an idea of how to go about this. I have a paper cup that's a cone shape, and then I know that the volume holds 650 centimeters cubed of liquid. I don't expect you to necessarily know the... Oh, wait, this is a cylindrical can. You already know how to do this one. I'm going to do this one. So 80 centimeters cubed. Sorry. Okay, so this is what we have. We have a paper drinking cup. So we have a piece of paper, and they fold it into a cone shape, and they make a drinking cup out of that. And they want to minimize the amount of paper that you need to make this drinking cup. And your drinking cup has to hold 80 centimeters cubed. These are fun problems, right? Not so much? Okay. Just imagine somewhere like making a paper cup in a factory. This is how we go about it. Okay, so on this one, look at the hint. I don't expect you to know the area of a cone because really this is lateral surface area, because on a paper, the area of a cone, you would have a top, right? So we're focusing on lateral surface area, which is just the area of the piece of paper. Make a cone, right? I don't have a lid on my paper drinking cup, so it's just the lateral surface area. So the area here, and I know this, so the area is pi RL. L is the slant height, which the slant height, if I come in here, if this is my height and this is my radius, this is my slant height. So the volume, do you guys know the formula for volume of a cone? One-third pi r squared times h. So here you can see I want to minimize this area function, but my area function involves an L, but my volume doesn't involve an L. So I need to write L as a formula of h and r, and then replace the h as a function of r from this. So this is kind of it's a two-step process. So what would be L in terms of H and R? So I have R squared plus H squared is L squared. So it turns out, and Wiley actually gives you this hint. So this is L. And if I plug L in for A, I would have that the A is pi times R times the square root of R squared plus H squared. So now I have a function of R and H. So I'm going to use this 80 equals 1/3 pi R squared times H. Solve for H. In terms of R, and then plug that in for H, and you have A in terms of only R. So what would this be? 8 times 20, what's 8 times 3? 24, what?
240.
Oh, 200, yeah, 24. Divided by pi R squared. So I have my A here is pi times R times the square root of R squared plus 240 over pi R squared, all quantity squared, right? So I want to simplify this to differentiate it, and I get R squared plus whatever 240 squared is times pi squared times R to the 4th. So if I find a common denominator under my square root, this would be pi squared R to the 6th plus 240 squared all over pi squared R to the 4th. So it turns out I can pull this out, and I have pi times R times 1 over pi times R squared times the square root of pi squared R to the 6th plus 240 squared. So the pi's cancel, and I have 1 over R times the square root of pi squared R to the 6th plus 240 squared. This is a lot easier to differentiate than this, right? So now that you have this, you differentiate this, set that equal to 0, solve for R. Question?
Where's the pi square root of 6 come from? Oh, you multiply, okay. Then
Yeah. Because everything's squared.
Yeah.
I will see you guys tomorrow.